system. We don't but use any quantum properties. But in future, even now, big labs in the US and many places, even in India, we are trying to make systems that work using principles of quantum mechanics. In particular, states types which have more quantum properties like entropy. So that's what I was trying to say, that it's a good improvement to do it for infinite dimensional systems, and the analysis also becomes more involved in the infinite dimensional setting. I think now I cannot say anything more without the slides. Meanwhile, if anybody has a question, you can ask. So basically, once you do the measurement, you get the classical system back, but you can do different kinds of measurements. It's not just one measurement. So now, what is the best measurement for a particular problem? That's a difference. So the different POVM, yeah, and it happens throughout in information theory that when you change to quantum information theory, at the end, the measurement becomes a big problem. Theoretically, you will say that there exists a measurement which gives a better performance, but how to find that measurement is also a problem. But more than anything, at the theoretical level itself, the availability of hundreds of different kinds of POVMs, which are measurements, makes this theory difficult. Different, not difficult, it's different. Yeah. Okay, so this is the kind of a result we are trying to show. Then what we do is that first you show this is also a very common theme in quantum information theory in general. When you want to talk about the behavior of a quantity over time or whatever, you first show an achievability result. Achievability result means that you show that there exists a strategy which gives you a behavior like this. That is the achievability of the behavior. And then you want to say it's an optimal strategy or optimal quantity. To show that, you want to say that there is no other strategy which can perform better than this. That is the optimality part. So when you want to show the behavior, you first show an achievability, that is there exists a strategy which gives you this result. And optimality is there is no other strategy which can give you that result. So these are mathematically represented usually by two inequalities. First you say that your latency is less than or is equal to some quantity. I'll come to this specific quantity, but first you show a less than or is equal inequality, and then you show some other opposite inequality. That's what usually we do. How much time do I have? Okay. Good. Now, so what Fanisa et al. Showed was that they produced a scheme of measurement and a strategy, and showed that first this happened. This is very easy. Just by the classic, you do one kind of a measurement, one strategy, you get a classical system, and classical theory says that you get an inequality like this. This is just because this is the classical relative entropy between the measurement outcomes. That is what this quantity is. You first show that, and then you take all the possible measurements and take the supremum of all these quantities. That quantity is written as d dash here, and from here, by considering that you have many measurements you can do, and taking supremum over all possible measurements, you can actually show that this tau min is less than or is equal to your this kind of a quantity. Here I'm skipping a little math here, in the sense that when you do these kind of joint measurements, you have to go to tensor product of filter spaces, where you consider all the states together and do measurements there, okay? And due to which you get these kind of quantities here. But at the end of the day, this idea of this slide is only that you produce a specific strategy and say that this your latency, the worst case latency, is less than or is equal to the sum up to some order of one terms is 1 over of the relative entropy. And then there are some results which was proved by Hayashi in 2001, which they used to converge to the limit they say that it converges to the usual relative entropy, which is the expected result. Okay, and that is the analysis for the achievability part. Now for our case, our first contribution in this paper is a generalization of this theorem to infinite dimension. So when I was studying this thing, I realized that if we have a generalization of a result like this to infinite dimensions, then we pretty much get the availability, achievability part. Okay, that is, you want to say that your this
so basically, you want to get the quantum relative entropy between two states using measurements. Basically, that's what the idea is. How can you achieve the quantum relative entropy of two states using measurements? That is Hayashi's result. You keep on doing for tensor products of states and then average it out, you will reach the quantum relative. That's a properly mathematical result. Yes, it talks about how to get quantum relative entropy between two states using measurements. That's what Hayashi proved for my dimensional states in 2001. And what we did first was to do that in data. So that's the first result. It says that if you keep on taking tensor products of states, the same states, for example, rho and sigma are two states, take rho tensor power k, sigma tensor power k, apply joint measurements here, and then you
the classical relative entropy between the output distributions and normalize them. At the limit, it goes converges to the quantum relative entropy. That is Hayashi's result, and then we proved that result for the.
So that is where real math comes. All the other things are similar to what is done in classical analysis, but what we had to use for getting there was
Things related to structure theory of one-on-one algebras, for the finite dimensional one-on-one algebras, and then later passing through the limit. That was the kind of idea which goes into proving Hayashi's result in the infinite dimensional setting. And that is where I think this talk fits into operator theory and operator algebras. It's a good time to ask.
Can you explain the quantum version of that
Quantum version of which? So basically, you have states rho and sigma, okay, and you take rho tensor power, here is L, right? L, and sigma tensor power L, and so this is what is known as the relative entropy, okay? So you have this, you take it to the L level system, you apply measurements. That is what is known as the joint measurement. Okay, joint measurements means you take tensor products and take measurements for the combined state. You do a measurement there, and then you get classical probability distributions. And these classical probability distributions do have a relative entropy, and that is what this quantity is. Okay, and then you divide that with L. Take L goes to infinity. Okay. This is equal to the relative entropy between sigma and rho. So This one, okay. So ML is a measurement at the LS stage. You just think of rho and sigma and apply a measurement m to rho and sigma, okay? And then when you apply the measurement, you get a classical probability distribution, right? After the outcome of the measurement is a distribution p sigma and here p rho and another distribution p sigma after the measurement. Okay. So perhaps we can discuss further later, but all I'm trying to say is that you get classical probability distribution once you apply a measurement, okay, on a quantum state. You get two distributions, and these two distributions do have relative entropy between them, and that is what this quantity is. And this is like a averaging out. It will converge to the quantum relative entropy between two states. That's what the Hayashi's result. And one. These are Hilbert space states, but one open problem here is to prove this result for one algebraic states, general one algebraic state. That's a good open problem actually. And also you can do QSM analysis for states on one algebra. That's also an open. Here it is infinite dimensional Hilbert space, and then you have a trace class operator with the trace tau is equal to 1. Okay? But now you can go to take a general algebra and consider states on that algebra. And then do this, ask the same question, change one question you can ask. Oh, yeah. So I need to wrap up, I think. So basically the main contribution is this result of this paper, okay? So I think I conveyed that. And the proof uses some, theory of, structure theory for finite dimensional one-dimensional algebras actually, mainly, and some CP maps and things like that. Not explaining. Yeah, essentially, Hayashi's result gives us the achievability part, and for the optimality, we don't have full proof yet, but we have a conjecture. What our conjecture says is that you are working with an infinite dimensional Hilbert space, you are getting states in there. Now, what we are trying to say is that you apply a compression to these states and bring it down to finite dimensions. Okay, the states that is a particular kind of measurement. It's a part of a measurement. You first bring it down to finite dimensions, and then there you apply the non-finite dimensional optimality, which is coming from Panisa-Karl's work. And now you go back to the infinite dimensions and try to prove the optimality. For doing that, we need to prove a specific inequality. What it says is that when you do this compression and do the theory in the finite dimensions, as you increase the number of dimensions, as n goes to infinity, the latency will increase to the required latency. Latency in the finite dimensions increase to the latency in the infinite dimensions. That is the conjecture which we have right now. If we solve this problem, this thing, we get the optimality aspect. Okay, so the theory lies there right now in the infinite dimensional system, where achievability is obtained, but for the optimality part, you need to prove this conjecture. So we don't know the answer to that. Thank you.
Thank you, sir. May I now invite Rajarama sir to the stage to present a token of appreciation to our distinguished speaker. Let's move to the next session. The chair for the next session. The chair for the next session is Professor Rajarama sir. I would like to say a few words about our chair. Professor B.D. Rajarama Bhatt is a prominent Indian mathematician and professor at the Indian Statistical Institute, Bangalore, specializing in operator theory, operator algebras, and quantum probability. He earned his PhD under Professor K.R. Parthasarathy and has made significant contributions to the quantum stochastic calculus and quantum dynamical symmetry, earning the prestigious Shanti Swarup Bhatnagar Prize in 2007. Now, I would like to call upon the chair, Professor Rajarama Bhatt, to introduce our next speaker, Professor Krishna Kumar Ji.
So, good afternoon, everyone. I thank Narayanan and Jason and all the faculties, Department of Mathematics, St.Aloysius College for this opportunity. So, what I am going to talk about is something called quaternionic spectral theory. So, it's basically we will be recalling all the functional analysis that we have learned in complex case. So here we will be dealing, instead of complex, we will be dealing with quaternions. The term you may be familiar with. Anyway, I will be explaining it. So this talk basically aims for all the beginning researchers, those who are working on various problems on complex operator theory. They can have a look at the classical problem they are trying. So what will happen in case of quaternionic case? So it's like whatever problem you are trying, you can try it in case of quaternions. Quaternionic operator theory, it's important because at around 1939, von Neumann showed that, and Birkhoff showed that the quantum mechanics can be formulated in case of real, complex, and quaternionic case. And as you know, the classical operator theory or the complex operator theory is stimulated from the problems from mathematics as well as physics, and it got its importance because its connection with quantum mechanics and especially the spectral theorem for unbounded normal operators. And here what we are trying to think about is how we have to develop this quaternionic operator theory as well as the quaternionic spectral theory. So quaternions are a number system that extends complex numbers, and it was introduced by Hamilton in 1843. And I say second point I have already mentioned. So the problem is like I will be showing you how this quaternionic operators are coming into picture, how quaternions are coming into picture, and what is its the difference in that the theory is while developing, what the difference it makes with usual complex operator theory. Okay, so there is the spectrum that we know in case of operators, complex operators. Here it's we call it as S spectrum. Okay, I will be defining it. So quaternions are a number system of this form, satisfying all these conditions, and it's basically a non-commutative, and we denote capital H as it's the real algebra. We denote capital H as the algebra of quaternions, and obviously there is a one-to-one correspondence with R4 to H, that is R4. Then if you have such a map, then you can have a R4, you can identify H with R4. And to develop the theory, we need these things like the real part of a quaternion is, if the quaternion is Q0 plus Q1i plus Q2j plus Q3j, then the real part of the quaternion is Q0. Similarly, imaginary modulus, the like Q bar, which is nothing but the conjugate of the quaternion. And this set is very important. It's Q1i plus Q2j plus Q3k, all the purely imaginary quaternions with modulus equal to 1. And you can see that whenever you have an element in S, this U plus SV, where U comma V belongs to R, is an isomorphic copy of complex numbers. And you can see that any complex number we can put inside a set of the form U plus SV, if we appropriately define U and V like this. And this is a term which we call it as, for any quaternion, we can have something called the two-dimensional sphere of that quaternion. That is nothing but whenever you have a quaternion Q, So we have something called a two-dimensional sphere associated with a quaternion. That is nothing but you can see that S can be imaginary part of Q by mod imaginary part of Q, and there will be an element of S. And something called axially symmetric. These are all the terms that we will use while developing the quaternionic operator theory. Okay. So we will start with what will happen with the quaternionic matrices. So we denote M and H as the collection of all quaternionic matrices, and like in whenever you have a matrix, first of all we have to think about eigenvalues, and in quaternionic case the eigenvalue like lambda x and x lambda are different because of the non-commutativity. Whenever x is a vector, quaternionic vector, and lambda is a quaternion number, so obviously we have to define the left eigenvalue and right eigenvalue. We have left eigenvalue, which is nothing but set of all lambda. Left spectrum is nothing but set of all lambda. Similarly, right spectrum. So then these are some results in quaternionic eigenvalues. It's been shown that every n by n quaternionic matrix has at least one left eigenvalue. It's like we can't apply the fundamental theorem of algebra here like an n by n matrix. We connect it with a characteristic polynomial and use the fact that it has exactly n eigenvalues with respect to including the multiplicity. Such theorem we can't take it here. Here things are a little different. So it's been proved that every n by n quaternion matrix has at least one eigenvalue, and it is shown that it is also proved that whenever you take an n by n quaternionic matrix and look into its eigenvalues, there will be exactly n right eigenvalues whose imaginary parts are positive. Imaginary parts are positive. Okay, and it's also been proved that let A be an n by n quaternionic matrix. A has exactly n eigenvalues up to equivalent class. It means that an eigenvalue of a quaternionic matrices can be infinite. Like if you take an n by n matrix, for example, you look into this matrix 0 I j 0, then it has only two left eigenvalues with 1 and I, whereas the right eigenvalues are 1 and all quaternions in the units in the open in the what is the term I have used, in the two-dimensional sphere of I. So it's like kind of infinitely many distinct right eigenvalues for a quaternion. So there is a theory that we can since every quaternion can be represented in this way, like every quaternion matrix we can write it like A1 plus A2j. A matrix which is called the complex adjoint matrix like this. We can have information 2n by 2n matrix. So from a quaternion n by n matrix, we can have something called chi A, which is a complex 2n by 2n by matrix. By complex, I mean that if we have a quaternion of the form q0 plus q1i only, we call it as a complex number. Okay, so we can get information regarding this is an example. So like the way how this chi A is formed. Okay, so you can work it out. So the result I wanted to show is we can whenever you have a quaternion matrix, we can have a connection with the chi A like this. Whenever A is invertible, A is equal to 0 as a unique solution. So we can have the chi A determinant chi of A is non-zero. So invertibility of a quaternion matrix and the invertibility of the chi of A, that is a complex matrix, can be connected in this fashion. So this is the result that is available. And now I will explain about what is a quaternionic vector space we will define. So there is a quaternionic right vector space. So it's like an additive group with a quaternionic right multiplication satisfying this property. Similarly, we have a quaternionic left vector space that is also an additive group with a left multiplication satisfying this property. Then comes a two-sided quaternionic vector space. So I am introducing all these things for the beginners, or I just wanted to make sure that you get the basics of what is in quaternionic operator theory, how the theory is being developed, and you can work by yourself whatever problem you can try in your hand on the complex case or classical problem that you are working, or you are motivated or you are extending, that all classical problem you can try in case of quaternionic operators. So what is exactly the quaternionic is, what is happening. So there is a quaternionic, two-sided quaternionic vector space. Then there is a right linear map on a quaternionic right vector space. Similarly, we can have a left linear map on a quaternionic left vector space. Okay. Then there is a norm we can define on a quaternionic right space, or the condition is. The only thing is you have to whatever condition in the scalar multiplication case, and there is a quaternionic left vector space, which becomes a norm in a quaternionic left vector space. How can you define the norm? So these are all this. Then quaternionic right Banach space. So with respect to norm, if it is complete, then Banach space, quaternionic right Banach space will come, quaternionic left Banach space. Then there is a something called a two-sided quaternionic Banach space. Then it should be both right vector space as well as left vector space, and as well as norm is defined in both these cases. And with respect to that, it should be complete. Then we call it as a two-sided quaternionic Banach space. Why I explained all these things, I will explain it in subsequently. You will came to know why this is important. So this is we can have bounded linear maps, right linear map, left linear map. When it become bounded, all these things. Okay. So a two-sided quaternionic Banach space turns into a real Banach space if you restrict the scalar multiplication to R, and it turns to a complex Banach space over CS whenever we restrict it to the CS. Okay, CS I have already defined. Banach algebra a two-sided quaternionic Banach algebra. So a two-sided in a quaternionic Banach space, we should have a multi. Why this? Suppose if we start the operator bounded linear operators on a complex Banach space, we start something like we start with a right Banach space and a right linear map. Then there is a problem like the collection of all right linear map on a right Banach space, quaternionic right Banach space won't be there will be some whenever you look into the whenever you trying to make it as a vector space, like a collection of operators won't make a vector space if we only consider right linear map on a right quaternionic right Banach space. We should have a two-sided Banach space. Then we should have the collection of all right linear maps. Then that collection of right linear map will become a quaternionic. I will for the time being I am just explaining all these things all of a sudden. I will give you the necessary references. You can go and work it out. The point that I wanted to make is the collection of all right linear maps on a right Banach space won't make sense. You should have a two-sided quaternionic Banach space. Then you should take the right linear maps. That will become the collection that we wanted to take forward to develop the theory. Okay, so and this is because of this reason. So just whatever I just explained, because of this reason, there will be some problem that whenever t times q you take, it won't be a right linear map. So we should have a two-sided quaternionic Banach space. So we develop the quaternionic spectral theory on an operator on a right linear operator on a two-sided quaternionic Banach space. Okay, so the similar theory you can apply for left linear operators. You should start with a two-sided quaternionic Banach space. You should take the collection of all left linear operators on that two-sided quaternionic Banach space, and that will form a quaternionic Banach algebra. And in this discussion, we take X to be a two-sided quaternionic Banach space. Bx is the collection of all right linear operators on X. Then Bx is a two-sided quaternionic Banach space. The operators on Bx, we call it as quaternionic operators. Okay, so the spectrum, the idea is we can have a left spectrum as well as a right spectrum. Both of them, this thing will fail to develop the theory. So up to 2004, who were working on this quaternionic operator theory were trying to identify what spectrum exactly makes sense in case of quaternionic case. So in 2006, they developed a spectrum which is called S spectrum. So S spectrum is the analogous spectrum that we need to develop the quaternionic spectral theory. The functional calculus and all will make sense with respect to this spectrum only. So what is an X spectrum? S spectrum is nothing but for an operator T in Bx and Q in quaternion. First of all, you should have something called the QQ of T defined in space. And with respect to this QQ of T, you can have the S resolvent spectrum, S resolvent set, that is of T, that is nothing but set of all quaternions where QQ of T is invertible. Then you can have the S spectrum to be sigma S of T, which is nothing but the complement of the resolvent set. And this operator QQ T inverse is called the pseudo resolvent operator. So the idea is, the fundamental idea is nothing but you can't have the left spectrum or right spectrum. You should have the appropriate spectrum for quaternionic operator is nothing but the S spectrum is nothing but S. Okay. So these are certain properties of S spectrum, that is nothing but both these sets, the S spectrum as well as resolvent are axially symmetric, and whenever the kernel of QQ of T not equal to 0, as in the complex case, Q becomes the right eigenvalue of T. Okay, so basically the S spectrum is nothing but the generalization of right eigenvalue, not the left eigenvalue. Okay, so like the eigenvalue to spectrum, like the right eigenvalue exactly will make sense more than left eigenvalue. So here also the set of all invertible elements are open in the unifying operator topology in Dx, and we can have the compactness and be bounded by this one, and we also have the spectral radius formula here also. So now what we were interested in is we were trying to likewise we were studying something called pseudo spectrum of a complex operator, and this is the definition of a pseudo spectrum of a complex operator. And why pseudo spectrum is pseudo spectrum is useful for the for understanding a non-normal operator, because spectral theorem you can have the complete information of an operator from the eigenvalues of the spectrum, but that is not the case of the non-normal operator. For example, if you want to understand about the norm of a non-normal operator, obviously you can't have that information can't get only from the eigenvalues. You need to go something beyond eigenvalues, and pseudo spectrum, which is found to be useful to identify the norm of a non-normal operator. So all the physical process, all the physical system, whenever while some numerical things or other way, whenever you are getting a non-normal operator or a non-normal matrix, in all these places pseudo spectrum found to be useful than the spectrum. So pseudo spectrum is used to study the behavior of systems that are not normal. So it is useful in stability analysis of dynamical systems, especially non-normal dynamical systems, study of non-Hermitian quantum mechanics, analysis of numerical methods to solve PDEs. All places pseudo spectrum found to be useful. So what we did is we find an analogous study on the something called pseudo spectrum of quaternionic operators. Okay, so there is also this is also another study that we have made. It's condition spectrum. Condition spectrum also is a kind of a generalization of spectrum, but what the difference it makes from pseudo spectrum is it is more algebraically close to the spectrum than the pseudo spectrum, that whatever the algebraic properties that spectrum follows, pseudo spectrum may not follow, but this generalization, that is nothing but the condition spectrum, it follows many algebraic properties that spectrum follows. And also it is why this condition spectrum, because of the definition, this is nothing but the condition number, and it's found useful in many areas. So what we did is, as I mentioned, we did the pseudo S spectrum of a quaternionic operator. So we have defined it like something like the S spectrum, a union, and the norm of the resolvent operator greater than or equal to 1 over epsilon, and for epsilon greater than 0. And I have mentioned certain properties that we have developed. We were able to develop a pseudo spectral mapping theorem, and the theorem is explained or proved as a set inclusion, and
we were able to characterize the pseudo spectra of rank 1 and rank 1 nilpotent quaternion operator, and we also use or identified or characterized certain quaternionic operators, pseudo spectra of certain quaternionic operators on Hilbert spaces. We were able to identify what is the pseudo spectrum operators, and also similarly we have studied condition spectrum of quaternionic operators, and we have defined in this fashion, and we developed certain properties of condition spectrum, and we proved some interesting result of condition spectrum, and condition spectrum of left multiplication, normal, self-adjoint, orthogonal projections are identified, and rank 1 nilpotent and rank 1 operators non-normal, we were able to do something. We were able to say something about the condition spectrum of such operators. So these are some of the work that we have done, and as I have mentioned, you can, whatever classical complex problems you are trying, you can have a look at the quaternionic case, what is happening. So these are some of the references, and this is the first reference basically say about quaternionic operator theory, and this one is this Sang paper say about quaternionic matrices, and this one is basically the complex condition spectrum. It says in this paper, Trefethen paper, it says about various applications of pseudo spectra, or it discusses many physical problems that non-normal system come into picture, and these are the papers that we were able to do, and thank you. Yeah, I think. I think that's what this in 1939 itself, Van Neumann and Vico has that you can form your complex and quaternions. So exactly, I think they have found that we can have such a equation that whatever nothing but we have said, we can. Yeah, I think no, I think we didn't go into that deep.
Thank you, sir. I will now invite Rajarama sir to the stage to present a token of appreciation to our distinguished speaker. Now we will have a tea break which is arranged outside. I request everyone to return to the hall by 3:45 p.m.
I can hear you fine. Thank you. No, honey. Mom was promised that she was fine. No. You want to no, you do it. Yeah, okay. Very well.
Let's resume this
Thank
issue.
you very much.
I call upon the next chair, Professor Krish. Before that, I would like to say a few words about our chair. Professor Werner Kirsch is a German mathematician and professor emeritus at the University of Hagen, specializing in mathematical physics, particularly in random Schrödinger operators. He completed his PhD in 1981 at the Ruhr University, Bochum, under the supervision of Sergio Alberio. His research focuses on the spectral properties of disordered quantum systems, including Anderson localization and Lifshitz trace. He has also contributed to the study of voting systems in the European Union, analyzing the distribution of power in the Council of the EU. Now I call upon the Chair, Professor Werner Kirsch, to introduce our next speaker, Peter Hislop, who will be joining us online.
Thank you very much. It was very
I hope that everything is okay because I lost any visuals there. So it's okay for you to start?
Yeah, so I'm supposed to introduce you, Peter. Peter Hislop is working at the University of Kentucky. He is also specialist in spectral theory and Schrödinger operators, including Anderson transition. He earned his PhD from the University of California, Berkeley. And as all of you know, important contribution to physics. Peter is, I'm happy to be a chair. Please go ahead.
Hello, I hope that it's okay to start now. I lost the visual, so I can't quite see what's going on there. Is it okay to start? Yeah? Okay. Yeah. Well, thank you very much for your patience. And here it's dark in the morning in Kentucky. The state of Kentucky is in the southeastern United States, where I've lived for quite a long time. Sorry I could not be there in person. I'd very much like to, but we're in the middle of our semester here. So it's a pleasure to present some somewhat recent results with someone who is there, my co-author, Fumihiko Nakano from Tohoku University. And I'm going to speak about random Schrödinger operators in a particular model in one dimension, which is called the random polymer model. And my talk is going to describe the so-called local eigenvalue statistics and the so-called phase transition in the nature of those statistics for this model. And this is what makes this model particularly interesting. And I'll just try to begin, I will begin, sorry, with discussing, scroll problem, sorry, with discussing random Schrödinger operators in general. I'll talk about the standard Anderson model and try to standard Anderson model and the so-called random polymer models. Models are interesting because they have a certain finite set of energies in the deterministic spectrum that are called the so-called critical energies, and they play an important role in the transport properties of these models. Since random Schrödinger operators are models of electron transport or of electron localization. So I'll talk about the so-called phase conjecture for Anderson and other random Schrödinger operators, talk about the transport and a measure of transport, and I'll talk about a conjecture, this phase transition conjecture, and I'll present it in terms of the eigenvalue statistics. And then to finish, I'll give a sort of light idea of some of the main aspects of the proof and some of the tools that I'm using these questions of transport and eigenvalue statistics for random Schrödinger operators. Okay, so let me talk about random Schrödinger operators. I'm only going to talk about discrete random Schrödinger operators, that is to say, random Schrödinger operators that are living on a lattice. And I'll talk in this overview about the d-dimensional square lattice, but I'll soon specialize to one dimension. A random Schrödinger operator, like all Schrödinger operators, describe a single particle and its interactions with its environment. The kinetic energy operator, since we're on a lattice, I'll describe with the letter L, and it's the finite difference Laplacian. So the finite differential Gaussian acts on functions in little L2, the square summable sequences on ZD, and it acts simply by summing over the values of the function at the nearest neighbors to the site. If I'm at a site n, I have the nearest neighbors and I have the values of those nearest neighbors. Very simple operator. The potential I want to focus on now is a random variable, and it acts locally on functions in little L2 of ZD, and it so it acts v omega on a function f evaluated at point k is equal to v omega at k times the function at k. And we're going to describe the omega of k in more detail on the next slide. What's really nice, and this was observed way back in the 1970s, about these operators and the analogous operators on L2 of R, L2 of RD, is that they satisfy a certain covariance property. And this covariance property is really fundamental for us to be able to talk about the spectrum of these operators. This H omega, which is L plus V omega, is a self-adjoint operator. In the situations that I'm considering, it's a bounded self-adjoint operator, but it's got a special property with relation to certain translations by a subgroup or the group of translations Z. Or some on the space of the random variables omega. So let's look at this a little bit more carefully. Let me move to the next slide. So again, some simple examples that I want to focus on. The original Anderson model, which simply says I have a countable family of random variables. That family I'll index by k. K is in ZD by space. And so at every point, the omega of k acts by multiplication by that random variable. And in this Anderson model, these family of random variables are independent of each other and are identically distributed. And the group which implements this covariance is the group ZD. So if you shift, when you look at the model, it looks identical, except with an action on the set of all random variables omega to denote this configuration. So if I choose omega out of a probability space, it fixes the potential at every site, and I have a self-adjoint. Now, early on, physicists realized that, oh, there's something interesting. Suppose that instead of looking at my Z2, or let me simplify, looking at my lattice Z, instead of looking at that, I look at Z, but I put together pairs of sites. And for a pair of sites, and that is what I'm going to call a columnar of length 2, I have a single random variable. And so this diamond model was studied in the 70s and 80s by physicists, and it's described in the following way. My random variables are pairwise constant in the sense that I fix the even site to n to be, let's say, in a value minus v and plus v, and at 2n plus 1, I have exactly the same random variable. So even one, and at the next odd site, it's the same random variable. So what happens when I wiggle, it wiggles a pair of sites, and the pair has a value either plus v or minus v with a Bernoulli distribution. It has probability p of being plus v and probability minus v, probability 1 minus p of being minus v. So let me see if I can draw a picture of this. So if I take omega 2n omega 2 n plus 1, a configuration might assign that with probability p being plus, next one over might be probability 1 minus p of being v minus. Right? So instead of having, I'll say these words, a rank 1 projector and rank 2 projector. And what they notice, as I'll describe on the next slide, is in this situation, certain energies, a discrete set of energies called critical energies, appear. So that is an example of a random polymer model where the polymer is the pair of sites, in this case, has length 2. One of them has value plus v, and the other has value minus v. And which one you get, a coin toss experiment, p could be a half, so the probability half, you're the polymer with value plus v, with probability 1/2, you're at the value minus v. Okay? Now, again, with respect to the subgroup 2z, so in all these cases, you have what's called spectrum. That is to say that even though each individual Schrodinger operator, h omega, its sum of its spectrum could change as I change this configuration of being plus v or minus v. There is a fixed set such that with probability 1, the spectrum of almost all configurations is that closed subset of the real line. So for example, the Daimler model which I described, that fixed set is minus 2d to minus v up to 2d plus v. It's an interval, and the minus 2d is in d dimensions the spectrum of our operator L. 2d minus 2d is in fact the spectrum of the deterministic operator, the fixed operator finite difference velocity in d dimensions. So I should think of this, as I tried to describe, this random Daimler model, as which I want to focus on now, 125, down here, as being, I make a choice on either plus v or minus v at 2 sites with probability 1/2. The next one on either minus v or plus v with probability 1/2. I have 2 Daimlers, one takes value plus v at 2 sites, the other one takes value minus v at 2 sites. And so for omega, I have just this random juxtaposition of plus and minus polymers of side length of length 2. So mathematical physicists are working on this. Realize right away that we don't have to restrict ourselves. Now we're working in one dimension to Daimlers of length 2. I could take 2 Daimlers with different configurations that are fixed. One will have length L plus, finite number of points and consecutive points, and the other one will have length L minus. So for a given omega, if I look at the potential on the real line, on ZD, the one-dimensional lattice, the potential is a sequence of Daimlers lying along the real line. If I look at it, I could get a plus. So I have L plus consecutive sites where I have some profile. So to write the profile, let's say L plus is equal to 4, could be some profile, but that is fixed. So that would be one polymer, and its potential is V plus. And then I could have another polymer with potential V minus of a different length L minus. And for any snapshot, so for any omega, the plus V minus V plus, V plus, V minus, V minus is strung along on the dimensional lattice of 2 different sites. So the case of random variables is the set of sequences of plus or minuses that tell me whether the next string is a plus polymer or a minus polymer, and that occurs with a Bernoulli probability, that is P in 0, 1. Let's say P is the probability that omega j is a plus, and 1 minus P is the probability that omega j is a minus. So that is the random polymer model. The choice of which polymer I encounter along Z depends upon a Bernoulli random variable, which is special. It makes the model difficult to work with, but makes it also very interesting. But it's written, the kinetic energy, if you will, is still the nearest neighbor, finite difference Laplacian, and V omega is now the string of potentials of polymers along the real axis. And the Gaussian model is a simple case where L plus equals L minus is equal to 2. And the two values are either plus B or minus B. So let's go on and explore some properties now of this random polymer model. So RPM stands for random polymer model. Sorry, let me go here. And I hope this is clear to everyone. Now, what the physicists noted by doing experiments and numerical experiments and calculations is that, as I mentioned, random polymer models have a finite set of discrete energies. So I'm going to call those energies script C subset. Spectrum. And if you look at a quantity called the exponent, the Elthuruth exponent is a well-known for people working in random Schrodinger operators in one dimension. It controls the decay of the Green's function of H omega. And if you take a critical energy for these random polymer models, the Elthuruth exponent is 0, which is quite unusual because mathematical physicists knew of something called Furstenberg's theorem, which states that for the Anderson model, let's say, the Elthuruth exponent is strictly positive for these one-dimensional models. And what that means basically is that the Green's function, so the Green's function is 1 over H omega minus Z, where Z has a non-zero imaginary part, that the Green's function, even as the imaginary part goes to 0, decays exponentially with probability 1. All of a sudden, you come to an energy where the Green's function no longer. What people speculated is that these critical energies are responsible for extended states of the system, because when the Elthuruth exponent is positive, the Green's function estimate be used to show that the solutions to the Schrodinger equation at those energies, so the solutions of H omega psi E is equal to E psi E, that these solutions psi E or K actually decay exponentially. And this is a key aspect of Anderson localization for the Anderson model, that you have pure point spectrum and the eigenfunctions decay exponentially, and the decay is controlled by the Elthuruth exponent. The Elthuruth exponent being equal to 0 means no decay, so you might think that the states are dominated by the generalized eigenfunctions of the kinetic energy operator L, and you might have extended states with non-trivial quantum transport. So to summarize, unlike the Anderson model, the random dyno and the random polymer models have a discrete finite set of energies called critical energies, where you don't see any decay of the Green's function, and consequently you might expect that these energies contribute to non-trivial transport And that's what we want to explore next. So what is a measure? Sorry, let me erase this. What is a measure of non-trivial transport? So in general, what you want to do is look at, for example, the mean squared displacement of a wave packet of a solution to a Schrodinger equation. So I'll just review that briefly here. You look at the given state, psi, which is an initial condition. And you might want to look at that state projected into a particular spectral subspace of H omega, let's say energies in an interval I, and then you look at the time evolution according to the Schrodinger unitary group generated by the Schrodinger operator. So this function is what I'll call a wave packet. Of course, it's a function of the index along the lattice z, but it is also a time-dependent solution to the Schrodinger equation. And we want to look at the evolution of this wave packet. Of course, the Schrodinger equation preserves the probability given by the initial condition, so the evolution is given by a unitary operator. And I want to ask the question, how does the randomness, which is encapsulated both in the spectral projector and in the operator H omega, affect the propagation? In particular, for the random polymer model, is the randomness at critical energies, if I localize an initial state near critical energies, does the randomness not affect the propagation and I get some transport? All right, so let's go on and look at that now. At least where I wrote here. To particular measure the amount of transport, I'm going to look at what I call the expectation of the position operator, or the key power of the position operator, the moments of the position operator in the wave packet, for the wave packet psi of t. And what people mean by a phase transition in the transport properties of a random Schrodinger operator is the following. There should be a finite energy E star, and let's suppose my deterministic spectrum starts at 0, so there should be a finite energy such that for all initial wave packets whose energy is localized in the interval, let's say E0, I should say, up to E star, the moments are finite, are bounded for all time. That is a signature of localization of the solutions to the Schrodinger equation. On the other hand, the phase transition says if I look at higher energies, as is illustrated in the second dot, in an average over time, the average mean displacement of the wave packet should grow in time. For example, it could be bounded below by a positive power of the time. And so this is the transition conjecture that for random Schrodinger operators, at least in higher dimensions, this original conjecture was made for dimensions 2 or higher, there should be a region of energy such that I start a wave packet with energy localized in that region, then all the moments of the wave packet remain bounded for all time. On the other hand, if I look at higher energies or energies near the edge of the deterministic spectrum, then there should be non-trivial transport in the sense that the average moment should propagate in time and be bounded below or unbounded in time. Now, for one dimension, it's well known in one-dimensional problems, the usual Anderson model, this does not occur. We always have localization. However, what was discovered by theoretical physicists was that for these random dimer models, we always have some transport. So for mathematical physicists, back in the 90s, Dept and Germain discovered for the dimer model where you have pairs, a dimer of length 2, that in fact, away from the critical energies, and I denote the critical energies by script C, for the Daimler model, there are two critical energies. If I look at my initial wave packet with energy localized away from the critical energies, we always have what's called dynamic localization. That the moments of the position operator, so x of q, that's this function here, are always bounded in time. They didn't solve the question of whether or not there is also transport if you look at an initial wave packet with energies localized near the critical energies. This was done a number of years later by Schultz-Valdez results. They proved that if I take initial condition, let's say I have my initial wave packet at site delta 0, remember I'm on the lattice, I evolve that state, then there is non-trivial transport. That is to say, time average moments of the position operator are bounded below by a positive power of time, meaning that there's transport for that initial wave packet. So this confirms what theoretical physicists had thought, that if I go beyond the Anderson models, but if I have Daimlers of length 2 distributed with a Bernoulli random variable, probability, let's say a half that I get VV, probability a half that I get minus V, that with probability 1, initial wave packets with energies that are localized near the critical energy have non-trivial transport, whereas if I localize the initial wave packet away from the critical energies, I have complete localization. So that is a one-dimensional model that exhibits the transport phase transition between transport and complete localization or the absence of transport. And it's this model that Schultz-Valdez actually generalized to the two polymers of like L plus and L minus that I want to talk about and that I worked with on this model with Fumihiko and Nakano. All right, so to continue a little bit more, let's talk about and summarize the results now for, sorry, I have to do one more thing, for the random Daimler model. What we want to do is rephrase the transport transition conjecture to a conjecture that involves the eigenvalues. And what are the eigenvalues, you say? Well, what I want to do is I want to take my polymer model and restrict it to a finite length, a finite string of polymers, which I'll call lambda sub L, a finite string of polymers. And I want to take my random Schrodinger operator for the polymer model, restrict it to that, just with cutting it off, restricting to a string of polymers. Then that operator has discrete stack. The expectation of basically the Laplace transform of the process of test function, and if it has the form on the right-hand side, it's called a clock process. Better known is a Poisson point process, and it's sort of diametrically opposed to the clock process. It describes basically an ensemble of independent variables that occur on the lattice, and we distribute it according to a Poisson point process in the limit that L goes to infinity. Using these 2 point processes, we're able to describe the same conjecture that I talked about for the transport of the system in terms of the local eigenvalue statistics. And here's the conjecture. If you take our E tilde to be localized in a particular region of energy or general model, then we expect, especially near the low energies or near the band edges of sigma, that the limiting point process is Poisson. If we look in a region where we expect the disorder to have a very weak effect on the transport of the unperturbed operator, the finite difference operator, we expect that you get a different type of limiting point process. And in fact, in higher dimensions, it was conjectured a long ago, which would be exactly the same as the canonical ensembles, the Gaussian orthogonal ensemble coming from random matrix theory. In one dimension, it should be the same as that clock process. In one dimension, it's possible for the random polymer models, because we already saw that there's some transport. In general, for the Anderson model, if you carry out this calculation of the local eigenvalue statistics, there's only localization and you only get the Poisson point process. So in higher dimensions, very little is known about this conjecture, and Professor Kirsch is going to talk about that, some joint work with Krishna on the three-dimensional random Schrodinger operator with Dept interactions, or perhaps as our legitimate talk. It turns out that in one-dimensional, in my work with Professor Nakano, we get a transition in the local eigenvalue statistics. So let me turn to that next. And here are the main results. So if nothing else, I hope you will understand that in one dimension, you have to do something different from the Anderson model. And the random polymer model, or the random dimer model, which is an example of that, have these special energies. And due to this, we both have a transport transition and we have a transition in the local eigenvalue statistics. And here are the main results that we recently proved with Professor Nakano. So we have local eigenvalue statistics away from the set of critical energies. The rescaled eigenvalues exhibit the fact that they behave basically like they don't know that there are other eigenvalues that behave like independent random variables, and it's well known that a collection of independent random variables, if you look at their statistics, the statistics are given by a Poisson point process. On the other hand, if we look at the local eigenvalue statistics that are centered at a critical energy, or the collection of critical energies, then in fact the limiting point process is a uniform clock process. So we have this transition in the local eigenvalue statistics for random polymer models. So the proof of this is rather long. It has many details. And let me spend a few minutes talking about some of the aspects of how you prove that the local eigenvalue statistics either are uniform clock statistics, which is a signature of delocalization, a signature of the fact that the model should exhibit non-trivial transport, or wave packets whose initial state is in an energy interval containing the critical energies, or conversely, that the limiting eigenvalue statistics exhibit Poisson behavior, and Poisson behavior means that the rescaled centered eigenvalues, centered away from the critical energies, actually behave like independent random variables. Which is quite remarkable. On a small scale, when I look at a string of polymers, so they have a finite length system, the eigenvalues are highly correlated, yet as I let L go to infinity, they become uncorrelated, provided them away from the critical energies. And I should just add that technically we need some conditions on the density of states for this operator. So I think if my time is right, I have about 9 minutes left. Hopefully, so I'll try to finish on my Eastern Daylight Time around 7:30. So let me, well, I wanted to state there is another signature of clock behavior. I'm sorry, I forgot this slide, which is something we also proved. And you might wonder, what does clock mean? Clock means that, unlike in the Poisson case where these rescaled eigenvalues sort of are distributed all over the real energy axis, and therefore, and behave like independent but Poisson distributed random variables, in the clock situation, the eigenvalue spacing between the j and the j plus 1 eigenvalues rescaled appropriately by what's called the density of states at a critical energy. As I take L to infinity, that spacing is fixed. It's rigid, and Barry Simon, because of working with circular ensembles, said that they're like spaced like hands of the clock on the hours on old analog clocks. So specifically, to just write down what that means, if you look at the eigenvalue spacing between the n plus first and the nth eigenvalue for the polymer of total length L, and you rescale, you use the density of states to study those, then the spacing down here multiplied by the density of states at our critical energy, that consecutive spacing limits to 1, meaning that the eigenvalue rigidly placed along the real energy axis. Okay. So the point was, the Anderson model in one dimension, the local eigenvalue statistics, when you take the limit, are always Poisson point process. You always have localization. There's no transport. But you can take a one-dimensional model and change the way the randomness is described through the potential, so that if you have clusters called polymers of, in this case, two different types of clusters, one is length L plus, the other one is length L minus, they're strung along the axis Z with a probability that's given by a coin toss, that is a Bernoulli probability measure. Then, because of the occurrence of critical energies, where the Lyapunov exponent vanishes, therefore nothing decays exponentially at those energies. In fact, you have a transition both in transport and in the local eigenvalue statistics. In the local eigenvalue statistics, if you're away from critical energies, you get Poisson. If you're at critical energies, you're centered at critical energies, you get clock, which means that looking at the points of that process, the spacing, rescaled spacing between eigenvalues is fixed. So how do you go about doing that? Just in the last few minutes, let me just give some key ideas. If any of you have studied, and I know some of you have, I know some members of the audience, if you study, let me move on, if you study these Anderson or these random polymer models, the distribution of the random variables is very important. In the Anderson case, if your random variable omega j is distributed according to a nice probability measure, let's say that's absolutely continuous with respect to the bag, then you get always in the one dimension on L2 or Z, you always get localization, and you have lots of tools to study those. If, however, you replace that with a Bernoulli distribution, so even in the Anderson model, if your omega k from the very beginning takes values +1 and -1 with p and 1 minus p probability, technically those models are extremely difficult to study because the probability is a measure, is a singular measure. So when you have singular probability measures, it's quite difficult. So the Anderson model with Bernoulli probability measures has been studied since the 80s, and I'll mention some work in a moment, and we need to use that work for the random polymer models also. But generally, what I tried to sketch here are some basic ideas. when you're looking at LES at critical energies, so you center your process at a critical energy, it's known from other work that not an easy, but a good way to approach that is through the Prüfer variable formulation of solutions to the Schrödinger equation. And there, you try to compute the characteristic function of the process for length L and look at the limit of that characteristic function. On the other hand, if you're looking at energies to center your process away from the critical energies, then there's a standard procedure going back to Yanni, and well known to people working in point processes, that you need, first of all, some localization bounds on the resolvent. That comes through the non-zero nature of the Lyapunov exponent. So you can control the resolvent, you can control the eigenfunctions. So you need the eigenvalue estimates and eigenfunction estimates. The eigenfunction estimates, there are two types. One is called the it's called the Wegener estimate, the other is the Yanni estimate after the Yanni, which we work on the Anderson model. And then you have to get information about the process itself and the use of the Bernoulli-Poisson theorem for a family of random variables where you're asking the probability that k of them have certain property and the rest of them have some other property with probabilities p or 1 minus p. That process will converge, the Bernoulli distribution converges to a Poisson point process. So two different approaches to the two characteristic situations that we want to study. And let me just say, for those who might be familiar, you can reformulate the discrete Schrödinger operator on Z as in terms of the transport operators. You can therefore look at the solution UN and U minus 1 as a vector, and you can introduce Prüfer variables. You can look at the Prüfer phase, which is theta sub L. And you notice in the middle sign is capital psi sub L of x as the Prüfer angle, which is comparing the Prüfer angle at a critical energy that's been perturbed away a little bit in the critical energy itself. You can rewrite the characteristic function of the process in terms of these quantities, the expectation of the sum over integers from 1 to L, it's our universe, a function evaluated at that, and then you have to carefully study the behavior of this as L goes to infinity. So that's just in a nutshell. I'm missing a lot of, skipping a lot of points for that. If you carry that out, which we've done, you prove that you get a uniform clock process. The other thing to finish up that I'd like to mention is that the challenges in looking at the localization side, or the Poisson point process side, is these eigenvalue estimates for the system, the polymer system of length L, so-called Wegener estimate, was studied for the Bernoulli-Anderson model back in the 80s by Komoda, Klein, and Martinelli, and they proved a very weak estimate of the probability that our finite length when the polymer model has an eigenvalue in some energy interval. The second thing we need is the probability that our finite length random Schrödinger operator has more than 2 energies in that interval. So we have to deal with 2 energies, which are 2 eigenvalues, I should say, which are highly correlated. This is something that Yanni did for the Anderson model in the 90s, but there was no known Yanni estimate for this Bernoulli type process, or Bernoulli probability measure, so we had to do that. The known results don't hold. And finally, something which I'll mention is that the integrated density of states is only wholly continuous, so you don't have a density for the density of states measured. That means that these random processes have to be redefined. This is again ideas which go back to humanity in the mathematical physics camp for applications of random Schrodinger operators. You have to filter these processes through the integrated density of states function, and this requires us to work with the unfolded local eigenvalue statistics. So this is something that was explored by Miyavi, but also by German and Klopp for Anderson-type models, and you have to adapt that machinery to these random polynomial models. So if you work out these things for the random polynomial models, we worked it out and we're able to prove, meaning Professor McConnell and I, we're able to prove that you have, for these models, this transition in the local eigenvalue statistics. So let me finish with that. At the end of these slides, let me move ahead. Just summarize those models there. There are, I mentioned some of the key references. I mentioned the Pomona, Klein, Martinelli article, Cole, Germanet, and Klein for humanities, for the local eigenvalue statistics for Anderson models on CD, the work of Dept and Germanet on dynamical localization for the random dimer models, other important works that we use, and then our preprint is on the archive there. Jitlamir, Sky, Schultz, and Stoltz, the work of extending the dimer model, improving delocalization for the random polynomial model, and Miyavi's groundbreaking work on local fluctuations for the multidimensional Anderson model on the lattice CD. So I hope you got some idea of development of random Schrodinger operators, random polynomial models, and this idea that even though in general in one dimension we only have localized states and dynamical localization and also point processes, if we modify those a little bit, we get good testing grounds for seeing that these conjectures for transport conjecture or local eigenvalue statistics conjecture are true for these models on the lattice in one dimension, and that some hope that the, for example, three-dimensional Anderson model has the expected transport transition, local eigenvalue statistics transition when we have a weak disorder. So thank you very much. It was a pleasure to speak to all of you, and I hope the conference continues well. Thank you.
So I'm afraid you can neither see nor hear us, but I will tell you about the so if you have questions, we will transfer it to Kentucky. Any questions? So then let's thank the speaker again.
Let me make a suggestion. If anyone wanted to ask a question, they could put it in the chat. I mean, also I can send the organizers these slides if someone would like to look at them, or you can email me. Oh, Werner. No, I didn't. I couldn't barely hear it. Thank you very much. Have you given it? No, I'm good here. Yeah, I'm sorry. But I do appreciate the organizers for allowing me to speak. And again, hope to meet many of the participants at another conference. Thank you. And you too, Werner. That's really something. Thank you. Thank you very much, and I hope you continue to have a good conference. Thanks again for allowing me to speak and bringing up. Yeah. Have a great evening. Bye.
Thank you, sir. The next talk will be the last talk of the day. Our next chair is Professor Krishna Kumarji. I would like to say a few words about our chair. Dr. Krishna Kumarji is an assistant professor in the Department of Mathematics at the University of Kerala, Karyavatam campus. He specializes in operator theory and spectral theory. Dr. Kumar completed his MSc and PhD in mathematics from IIT Madras and has held postdoctoral positions at ISI Bangalore and the University of Manitoba, Canada. He has received the Kerala State Young Scientist Award in 2018 and is currently guiding 5 research scholars. I welcome the next chair, Professor Krishna Kumarji, to introduce the last speaker of the day, Professor Shankar P.
So this is the last session, and we have with us Dr. Shankar P, who is the assistant professor in the Department of Mathematics, Cochin University of Science and Technology, and who have completed his PhD from Kerala School of Mathematics, Calicut, and done postdoc in ISI Bangalore, and his area is operator algebras and operator theory. So I welcome Shankar.
Hello, yeah. So, thanks for the invitation. I especially thanks to Narayan and Jason and the organizing. So let me start when that slide comes. Maybe before that, I will just, without proper definition, I will introduce what is the convex set. Okay. So the convex set means, so if you take in the complex plane, so if you take some this kind of thing, so this will be convex. The convex means if you take any 2 points and you join them by straight line, that line has to be inside that set itself. So that is the thing. But if you take set like this, so this set won't be convex because you can obviously see you take 2 points and you join the straight line connecting them. It's not completely inside the set, so this is not a convex set. So now we are going to study some special kind of operator, the range of special kind of operator. There is a Bayesian transform in functional Hilbert spaces. The functional Hilbert spaces are RD space and the Bergman space, and you can have Fock space and Dirichlet space. So now we are going to examine in that some of the operators, the Bayesian range of some of the operators, whether when it is going to be convex and all. So this Bayesian transform, it was introduced by Bayesian, but the thing is that they study the property of Bayesian transform and to know whether the operator is invertible or you can detect the compact, that means the operator theory property of the operators. Okay, so that means they didn't study the geometric theory point of view, so whether how the range will look like. But because this set will come already, Professor Jayadev introduced numerical range, so this set will become a subset of numerical range, but numerical range is always convex by the Toplick-Saustroff theorem. But whatever we are going to study the Bayesian range, it need not be the convex always, but with some, we can give some characterization for some of the operator, composition operator, multiplication operator, and Toplick's operator. So when we can make that is convex, so in some RD space and Bergman space and even Fock space and Dirichlet space, that's what we are going to discuss. So once this comes, then we can start like this.
Okay. So now I will start with the definition of reproducing kernel Hilbert space. Suppose you take any set and we can say that the functions collect the functions from all the functions from X to F. So then we can take a vector subspace from the function space and you end up with inner product. So that inner product, then we can make them as a Hilbert space. After that, making as the Hilbert space, because you ensure that the evaluation is functional, that is bounded. Suppose if these properties are satisfied, then we can call this Hs here reproducing kernel Hilbert space. So then, like when you have a Hilbert space, the well-known theorem, Rees representation theorem you have, using that, what you can do, you have this is going to be a linear functional. This linear functional, you can have the vector. You can get the unique vector kx. So you maybe y, then we can call it kx. This is called a reproducing kernel at tx. I think then you normalize that because we want this kx cap norm 1. Because of that, you normalize that, then kx by kx cap. So now this is a normalized reproducing kernel. So now if you take any operator, boundary linear operator t acting on these function spaces, now our Hilbert spaces are going to be a function spaces. Okay, it's not going to be a that equivalence class of function spaces, that we are not considering. So you take a linear operator on the Hilbert space and you consider Bayesian transform. You consider this one. So you take t kx cap where x belongs to x. So this kx cap this is a unique vector given by the reproducing kernel. Okay. Yeah. So next, So okay. Initially, Bayesian transform is defined like this. So when you have Bayesian transform, this is the Bayesian transform. We want to study what is the range of this thing only. Do the property of convexity property of this range. Then there are notions about Bayesian radius also when you take the supremum over this set. But we are not going to take that part. So we will mostly concentrate on this set. Okay. So first, Bayesian introduced this transform to do many things because it has helpful for, I already told, detecting the invertibility and the compactness of the operator. And one more peculiar property is that if you have two operators, they are equal, okay, then the Bayesian range is equal. The Bayesian transform is equal at each point x, then we can say that the both of them are equal. And this gives essential information about your operator. Yeah. So now that Carrel in 2006, he formulated this Bayesian range, and he also that time also he is not looking into its convexity, but he only looked into the Bayesian range, how the Bayesian range look like. So then you have numerical range, but you just to see numerical range here we are taking all the unique vectors in the Hilbert space, but there we are taking only reproducing kernel, so kernel vectors. So that means all the kernel vector will be, if you take norm as make as a unique vector, that will be the unique vector, but it will not cover the all the unique vectors of the Hilbert space. So this is a numerical range. So then from this you can obviously tell that this is a convex already mentioned by Tropik-Hausdorff theorem. So Bayesian range is always going to be a subset of numerical range because of this one. So now what you do now the question, this is a basic question. So whether given operator, so because then this is a subset of a numerical range, but when you can say that the Bayesian range is convex. So when you can say that the Bayesian range is convex. So that is the main question of we are going to answer in this talk. So next, so I think this that is the thing. This is the first time, recently only the geometric viewpoint study of this Bayesian range is started. Okay, so then this was not initiated, but first initiated by Carrel on the model space on model operator. Okay, first he gave an answer for model space on the model operator, but I will come to that what is this one later. So then later this recently these Kurz, Cohen and Felder, they characterized some of the operators, some composition operator and the multiplication operator and some matrices. They found what is the Bayesian range for matrices and all, multiplication operator and all, and they proved that some of the composition operator, when they are going to be convex, the Bayesian range is convex. Yeah. So now for the sake of finite dimension for understanding, you take Cn. Cn we can view as just two functions from points on the n set to C. Just a functions from here. So So Cn you can make this as a reproducing kernel Hilbert space, and the reproducing kernels you can take this EJs, that standard basis, orthogonal basis you can take. So now if you consider, you take any matrix, you consider the Bayesian range of this one, it will give only the diagonal elements. So the obvious choice is when it will be convex. So when it will be convex, suppose the discrete points are convex, they have to be same. Okay, you cannot be the convex that will be there. So because of that, a matrix has to, if you take a matrix, then Bayesian range is convex, then it should have a constant diagonal. If you take any matrix, it should have a constant diagonal, then you can say that, so this is your Bayesian range is convex. So, but here one property lacking is when you have a numerical range, so that you, suppose you take T1, T2, two operator, and if T1 is unitarily equivalent to T2, so then the numerical range of T1 is equal to numerical range of T2. So this is true. Up to unitary equivalence, they equal so. But the Bayesian range is not the case. So it is not, we can give an example in finite dimensional itself. You take A and B, these two matrices, they are unitarily equivalent with this unitary operator. But Bayesian range of this one is 1, 2, and the Bayesian range of the C is you can get a singleton point. So because of that, the unitary translation is not there. Because of that, it is very difficult to handle also, not like the numerical range. Yeah. So next we can go to the multiplication operator. You take, you can say this is a multiplier algebra, but you take all the GF, if you take a Hilbert space H, GF such that you collect all G such that GF belongs to F for all F. So this is multi of G. We define multiplication operator on any reproducing kernel Hilbert space we can define. It's not a problem. Then M of GF with this multiplier. So M of G of F equal to GF. So now this Kahn and Felder proved that, so this multiplication operator, the Bayesian range of multiplication operator is convex if and only if the range of this function G, so that is convex. Suppose this is convex and this is also convex. This is just a simple computation using the reproducing kernel. So this is a one step, you can write it, you can get it. So next thing is we want to go to the, because now here it is true for any reproducing kernel Hilbert space. It's not particularly you want RD space or Bergman space, anything. It is true for any reproducing kernel Hilbert space. So next we want to go to the particular spaces. So now you take composition operator. You can define this C phi of F equal to F of phi of X. So suppose you take, maybe you can take from D to D. So your phi is a self map. You can define C phi of F of some X equal to. So this is nothing but you can take F is some functions from D to C. You collect all the functions. So F such that. So you can define this is nothing but F of P of X. So just I didn't write X. So this is a definition of composition operator. Yeah. So now we want to detect whether this composition operator, the Bayesian range is convex or something like that. But yeah, I will come to RD space proper definition. You can take RD space is nothing but set of a holomorphic function with the coefficients. You have that as a scalar series expansion with the coefficients is a square sum of it. Okay, you can take this H to D. So in that, this is kind of elliptic symbol. Elliptic symbol, it's an automorphism. So you take T from the unit circle T, then the Bayesian range of C phi is convex, then the psi has to be either 1 or minus 1. Okay, if and only. So this one next for the Blaschke function, like it's a Blaschke factor. So then when the Bayesian range is convex, then the alpha has to be 0. So this is also Cohen and Felder proved on the RD space. Okay. So then the model space, I just defined, you take any inner function. So inner function means, for the sake of definition I am saying, inner function means as a geometric point of view, we take interior of the disk to disk and boundary to boundary. So that keep the simple. So now you define k theta, this model space, h2 minus theta h2. So then you can define a multiplication, that means you take S is here, right shift operator, then you can define model operator. You apply k theta and project it back to the k theta. So p theta is there, orthogonal projection to this one. So now here, this is a reproducing kernel. For this is a reproducing kernel Hilbert space. This is a reproducing kernel. So here, so what Karev found out is this Bayesian range of this multiplication operator for theta equal to Zn. This for this inner function, it is not only convex. He exactly found the range. That is nothing but disk with the radius n minus 1 by n. Okay, this is a disk with the radius n minus 1 by n. Okay, so now from up to this only in the literature note, now whatever I am going to say, it's our contribution to this direction. So like in the finite dimensional thing, you can have L2 space. L2 space means you take a sequences, square summable sequences. This you can consider as a functions from point the natural numbers to C. So here the means orthonormal basis, you can take EJs on orthonormal basis, but the thing is that this is also going to be the kernels, okay, reproducing kernels. So here also you can say that Bayesian range will be AJJ, only diagonal elements will come infinite, but here also it's a discrete set, then it has to be a single element. So then this infinite matrix also you should have a constant diagonal to be the Bayesian range of this A has to be convex. Yeah. So next, yeah, I already told what is order space. This is your order space. You take a holomorphic functions and the coefficients are square summable. So this is your order space. Then you take a reproducing kernel like K W of Z equal to 1 minus W of Z. So this is a reproducing kernel on the order space. So now quickly I will go through. They actually Carrel, they did it for only that alpha from T, but because we can take a composition operator, because for the RT space you take any self-analytic map. So field from D to D self-map which is analytic. Okay, for any self-analytic map, the C phi is bounded. The composition operator is bounded because we cannot talk about here unbounded operator. So this is bounded. So because of that, yeah. So because of that, I will take alpha from like D closure. So then you consider this phi and you consider your composition operator. So then this Bayesian range of this is convex. Then the alpha has to be from minus 1 to plus 1. It's in the line. So minus 1 to plus 1. Okay. So now, yeah. So now this is the thing you can consider. Suppose if you take alpha in the minus 1 to plus 1, this is always coming like a straight line. It's a convex. But if you take other than that, so you consider if you take any element other than the real line from the disk, you can see this is not convex. Yeah. Okay. So now we will go to examine the Topics operator also in the RD space case. Okay, you consider Topics operator with the T phi of F equal to P F of phi F of P into the unit disk, and you can explicitly write d tilde of r theta is nothing but using this expression. Okay, so here for the Topics operator also it is coming that you can compute it. So if a Topics operator, Bayesian range of Topics operator is convex, if and only if this P tilde W, this set has to be convex. If this set is convex, it is convex. It's coming like multiplication operator, but this cannot, their multiplication operator is for any Hilbert space, but here you cannot do it for any Hilbert space, here it is only for the RD space. Yeah. So now, so next what we want to do is, we want to do at least finite rank operator. So instead of giving something, whether finite rank operators, whether what we can do. So you already Carrel, he gave us one example. If you take finite rank operator of this form, then you can always get Bayesian range like this, 0 to 1 by 4, you can exactly get this one. So now we want to try what about if you change Z. So when you take Z power n also, the Bayesian range we can compute like this. So now we want to improve like this. So instead of Z power n, you give some coefficients, A is Z power I, A is Z power I. So then you consider this finite rank operator. So in this finite rank operator also, we can able to prove this Bayesian range of this AN is convex. But the thing is that in this form, if you take the operator, finite rank operator of this form, but we could not able to find the Bayesian range exactly here. But when your AI, so suppose your AIs are constant, so this and this AIs are same A, if you give same A, that time we can able to find out exactly what is the Bayesian range. Yeah. So yeah, from compact finite rank operator, and this is also not covers all the finite rank operators, it's kind of particular form, and we have next to move to the compact self-adjoint operator. So if you take A Z and A Z power n, you have this and this same, that time also we can able to prove that for the compact self-adjoint operator also Bayesian range you can have 0 comma mod A square, then this is convex. Okay. So next, yeah. So next one is, yeah. So now what we can do, instead of a z power n, a z power n, we can change general analytic function. The general function belongs to z2, that means RD space. This is also a finite rank operator. Then we proved that this is Bayesian range also convex, if you take like this. Yeah. So, but when it will not be convex? We want an example, because all the places we consider this and this are same. But when you take different GI and here something different, what will happen? So that time we got an example. Suppose you take 1 plus z and 1 plus z square. This is a rank 1 operator, but for this rank 1 operator, you take two different things here, but it's not convex. We proved that this is not convex is coming, but maybe you may need some characterization to prove that, but that is still open what is that. But the thing is that when you have rank 1 operator of this form, z power n and z power n, this is different. So this time we can able to compute the thing is that Bayesian range. That time the Bayesian range will come like a disk of radius this one. Okay. Still now we got all the things are interval, because all the things are self-adjoint operators. But here it won't be self-adjoint, because of that we are getting this disk of radius, this one, the Bayesian range. Yeah. So next we want to move to Bergman space. So Bergman space, you take all analytic holomorphic function with square integrable finite and with this normalized area measure, and here also this is also reproducing kernel Hilbert space, and the kernel will be just 1 by 1 minus w bar z square. So this is a reproducing kernel. Yeah. So here again we will consider composition operator, and because here also this is true. If you take composition operator, when phi you take self analytic map, all the composition operators are bounded. So here with this we can have, first we will have this symbol like phi of z equal to alpha z, where alpha belongs to D closure. So here also we got similar thing like so then this is convex if and only if, then we have that alpha should be -1 to +1. So now, and you can have directly you can come to elliptic symbol. So alpha is a phi of z equal to alpha z, or alpha belongs to the unit circle mean. This is actually an automorphism, this elliptic automorphism. Here we are getting that alpha Bayesian range of C phi is convex, alpha equal to 1 or -1. Yeah. Okay. So here also you can give example where if you don't take between -1 to +1, then it is not convex. You can give this diagram. Yeah. So next we want to go to the Blaskey factor. So if you take a Blaskey factor also, because to prove Blaskey factor it is not easy, but it's not straightforward. You have to prove some geometric properties of the Bayesian range. So first what we proved that the Bayesian range is closed under complex conjugation. That means it will be symmetric about your real axis. Suppose, so if you take a point, suppose this is there, if this point is there in the Bayesian range means, then this will be also, it will be there. Okay. It is symmetric about the real axis. Yeah. So then if you take any so if you take any point in the Bayesian range, then the real part of that the Bayesian range also, the real part of that element also should be in the Bayesian range of C phi. So using this result, we can prove that the Bayesian range of C phi alpha on the Bergman space is convex if and only if alpha has to be 0. So this is it. So this we prove. So actually there are a lot of questions over here, because why? Actually we did for only particular kind of automorphisms from D to D, that is also elliptic and factor. Even suppose you take, we did it for what? P of z equal to some lambda z, where lambda belongs to unit circle. Okay, so this means T you can take, so then P of z equal to, you can take z minus a by 1 minus a bar z. So like this, only this thing only we prove. Actually even we don't know the answer for the combination. You take any automorphism from disk to disk, it will be of the form P of z equal to lambda into z minus a by 1 minus a bar z. Okay. For this question itself, we didn't have answer for this. When it will be convex. Even you can take, because this is an automorphism. Other than automorphism, there are a lot of analytic maps from D to D self maps are. Okay. So all the things is still open. Okay. To finding the Bayesian range. So even you take, so P of z equal to So you take z minus a by 1 minus a bar z and int. So z minus b by 1 minus b bar z. Okay. So now for this also, this is called Blasket. This value p tilde, there it's come, or this value p tilde, there it's come harmonic extension, but here we are taking this integral value as your p tilde. So then we can prove that so the Toplic Bayesian range of this Toplic operator is convex if and only if this range of this one is convex, this set is convex. Yeah. So this one. So again we continued the finite rank operator like that. There also here. Okay, fine. Yeah. So here also we can do the same analog thing what we did in the Hilbert space, in the Bergman space also. You take so for the we can compute this one. For if you take rank 1 operator of this form, then you can have Bayesian range as a interval like this. And you have, if you take GI like this, then here we proved that Bayesian range is convex, but we could not able to find exactly what is the range here. But again, again I told you like similar case, you can have an example of this rank 1 operator where the Bayesian range is not convex. Yeah. Okay. So here also the same thing. Like if you take the rank 1 operator of this form z power n and z power n, which is something different from these two places, that time also you will get a Bayesian range is disk with the radius of this quantity. Yeah. So next we will go to the Fock space. So you take a Fock space over C. This is nothing but Gaussian square integrable entire functions on C with the Gaussian this measure. You take this measure. So now this is F2C. This Fock space is a reproducing kernel Hilbert space. With the reproducing kernel will be exponential of ZW bar. So this is the thing. Yeah. So now here, but here the bounded that in the RD space and the Bergman space, if you take any self-holomorphic function, analytic function, the composition operator is bounded, but here it is not the case. So if the composition operator is bounded on the Fock space, the P of Z has to be like this, lambda Z plus A in this form. Okay. So that is the thing. Suppose this mod lambda, suppose it will be mod lambda strictly less than or equal to 1. Suppose mod lambda equal to 1. So then the C5 bounded if and only that A has to be equal to 0. Even in this case, what we able to prove is, we proved for P of Z equal to psi Z. Suppose with the plus A is 0, that time we can able to see that the Bayesian range is convex if and only if the zeta belongs to -1 to +1. But the thing is that when you put a plus A inside, so then when you take phi of Z equal to lambda Z plus A, that is still open. We could not able to continue. But maybe we can give value some, for A some value, then we can able to find the range. So but we cannot able to conclude the using that this thing diagram, we cannot able to conclude. So that is also open here. Yeah. Yeah, that is also open here. But if you take this zeta is in declosure, but if you take only on the unit circle, you can have this zeta is +1, -1 and +1. So this is the thing. Yeah. Okay. So now you can see if you take other than that interval +1 -1, this diagram is coming like that. This is not convex. Yeah. So next we move to the Dept space. So Dept space, you take functions of, so 1 by pi this square integrable functions with the dA is the Lebesgue area measure with this, and this is again reproducing kernel Hilbert space, and you will have reproducing kernel as kwz equal to 1 by z bar w log 1 by 1 minus w bar z. When w is non-zero, but w is 0, then it should be 1. So that is the reproducing kernel for this Dept space. So now, yeah. So here also we tried for this composition operator. Yeah. So here the composition operator, you take psi z belongs to d and the psi belongs to the t, the unit circle t. But here also zeta. Sorry, this is zeta. So when you take here also zeta inside that full unit disk, but it is not, the composition operator is not bounded. The result is that the zeta has to from the unit circle, then this composition operator is bounded for this this phi, this self map. So now here I think this is our computation to show this, but we will go to directly to the result. So here also we proved that suppose your Bayesian range of C5 acting on the Dept space is convex. So if and only if the zeta has to be plus or minus 1 in the Dept space also. And here also we can check for, because in the R space there is no only P of Z equal to lambda Z plus A, there we cannot have Blaskey function, but here we can have a Blaskey function. So this is an automorphism from D to D. You have this one Z minus alpha by 1 minus alpha bar. So for this one, so here also we can able to conclude using that. So the C5 Bayesian range of C5 alpha acting on D is convex if and only if this alpha equal to 0. Okay. Yeah. So now if you take other than this psi like that, you will get diagram. So like this. So that is the thing. So now, okay. So actually this is the paper. Actually there are 3 papers. In that some part I took it. So this is the paper I have Bergman space result about convexity. And you can have, this is a Bayesian paper introduced this Bayesian transform. And this is the paper which motivated to do this recent paper. This is a very nice paper, you can have it because there are a lot of problems also given. It kind of survey and they did it like this also. Many connection with the Bayesian transform also. This convexity of Bayesian range. So yeah. And the Carrel paper is, so this one, Okay. Yeah, this one. So here he started finding out the Bayesian set. And when he is finding, he didn't know that the convexity we can, he just gave some example, but then these Karlscoven and Felder, they started to doing this one. So now we continue up to this. Yeah, thank you.
Any questions? So there are no questions, and Shankar, thank you Shankar, and you have mentioned a lot of open problems, so you can try that one. So on behalf of everyone who presented here, I thank Shankar for a wonderful talk.
Thank you, sir. I would like to invite Professor Krishna Kumarji to present a token of appreciation to our distinguished speaker. Thank you all. This concludes the talks of the day. Next up, we will have the contributory sections. They will be conducted on 2 venues. Venue 1 is this hall and venue 2 is on the first floor. The chair for venue 1 is Professor Krishna Kumar and for venue 2 is Professor Kiran Kumar.